Hi, I'm Colin. In this module, we're going to sketch the quadratic function f of x equals x squared minus 2x plus 3 using two different approaches. In one approach, we identify this function as a shift or translation of a simpler function. And in the other, more standard approach, we calculate some essential features of the function, such as the concavity and where the graph cuts the x and y axes. This is a follow-up module to the one titled Revision of Functions, Finding the Domain and Range of f of x equals x squared minus 2x plus 3. If you haven't watched that module yet, you should go watch it before you watch this one. As a summary, in that module, we first revised the basic notions of functions. We then reasoned that the set of all possible inputs for this function, that is, the natural domain, is the set of all real numbers. We also showed how completing the square on this quadratic allowed us to more easily deduce the set of all the resulting outputs for the function, that is, the range. There, we worked out that the range was the set of all the real numbers greater than or equal to 2. In other words, this quadratic function will only output y values greater than or equal to 2. Finally, we finished off by saying that the range is most easily found by sketching the graph of the function. Now, looking at the graph, it is quite easy to observe that the function indeed only takes y values greater than or equal to 2. Moving on. It's important to note that the graph of any quadratic function is called a parabola. So here, this curve is an example of a parabola, and we can say that the curve is parabolic in shape. So given the formula for the quadratic function, how do we sketch its associated parabolic curve? What are the methods involved? First of all, notice that the vertex of this parabola, which is where the parabola crosses its axis of symmetry, is located at the point 1, 2. Now observe that the x value 1 and the y value 2 also seems to appear in the formula for the function, in the form after you complete the square. This is not a coincidence. In fact, completing the square not only helps you find the range of the quadratic function, it will also directly tell you where the vertex is. And knowing the vertex is one of the key tasks to sketching a parabola. But more generally, the values 1 and 2 represent more than merely the x and y values of the vertex. In fact, this formula tells you that this graph is precisely the graph of the simple quadratic, f of x equals x squared, that has been shifted or translated 1 unit to the right and 2 units up. So the numbers 1 and 2 in the formula actually represent the amount of horizontal and vertical shifting of a much simpler function. This motivates a general piece of theory on the shifting of functions, which can be a tremendously useful skill for the sketching of graphs far beyond just quadratics. It goes like this. Suppose you're given the graph of some function whose rule is given by y equals f of x. In practice, you would hope that this is a fairly simple function that you can sketch without much trouble. We're then going to make two small modifications to the formula. The first of which is to replace x wherever it occurs in the formula with x minus a constant, say k. The second thing we're going to do is to add another constant c to the formula. Then this new, more complicated function has a very special relationship with the original function, y equals f of x. And that's that they both have exactly the same graph. In fact, the only difference is that the graph of the transformed function will be the graph of the original function that has been moved or shifted or translated k units horizontally and c units vertically. Wow, that might have been a lot to take in at once. Let's see how all of this theory ties together with the quadratic function we've been looking at. We start with a function y equals f of x. Which I'll choose to be the simple quadratic function f of x equals x squared. Being the simplest quadratic function possible, you should be able to sketch this function without many problems. Now, choosing k to be 1 and c to be 2, we're going to transform this function in accordance with the above theory. This means we're first going to replace x wherever it occurs in the original formula by x minus k, which in this case is 1. Then we're going to add c, which here is 2, to the formula. The theory above then tells me that the graph of this transformed function is exactly the graph of the original function that has been shifted 1 unit to the right and 2 units upwards. Overall, this is a powerful piece of theory because it can be used on any function, not just quadratics. In fact, you'll probably find that quite a few complicated functions that you'll encounter in your mathematical studies, which at first sight may seem very scary to sketch, really are just simple ones that have been shifted. And by understanding how the shifting works, you'll be able to work out which simple function you need to sketch first, and by how much you need to shift this simple function by to get the one you actually need to sketch. In other words, if you can draw simple graphs, often you'll be able to draw their more complicated cousins with little extra effort. Isn't that brilliant? It's important to note that not every quadratic function has to be framed in terms of transformations in order to draw their graph. Here, we've simply used this particular quadratic to motivate and illustrate the general theory behind shifting transformations, which can be applied to any function. But coming back to quadratics, it's important to note that a more routine method for sketching quadratic functions involves doing some simple calculations to deduce the key features about it, such as its concavity and where it intersects the x and y axes. So what we're going to do now is state each of these key features, along with some general facts about how to find them by referring to the most general quadratic function possible, f of x equals ax squared plus bx plus c, where a, b, and c can be any constants. And then we're going to apply that to our particular quadratic, f of x equals x squared minus 2x plus 3. After deducing all of these key features, we can then sketch the graph. First up is concavity. As you know, the graphs of quadratic functions are called parabolas, but this could be a smiley face parabola, called a concave up parabola, or it could be a frowning face parabola, called a concave down parabola. Generally, it's the leading coefficient, that is, the number multiplying the x squared, that determines whether the parabola is concave up or down. Specifically, if the leading coefficient is positive, then the parabola is going to be concave up. And if it's negative, then the parabola is going to be concave down. For our quadratic, the leading coefficient is implicitly 1. Since x squared is really 1 times x squared. 1 is certainly positive, so we have a concave up parabola. Secondly, we should find the vertex. You may recall from earlier that transforming this parabola by completing the square will reveal the vertex, but there is a direct formula for the x value of the vertex also. That formula is x is equal to negative b divided by 2a. That is, the negative of the middle coefficient divided by twice the leading coefficient. Here, that would be x is equal to negative of negative 2 divided by 2 times 1, which gives just plus 1. Now, the vertex is an entire coordinate, so we need the y value too. So we simply substitute x equals 1 back into the function, and that will give us 2. Hence the vertex will be the point 1, 2. Which confirms what we already knew from our earlier investigations. Thirdly, it will be useful to know the Y-intercept. Which is where the graph will intersect the y-axis. The key observation here is, when you're on the y-axis, the x value will always be 0. Thus the y-intercept is simply given by the function when evaluated at 0. Here, evaluating f of 0, we get 3, which is precisely the constant term in the quadratic, since all the terms containing x will become 0. In general, the y-intercept of any polynomial function will always be its constant term. If you have never heard of the term polynomial, don't worry yet, you will soon. Finally, you might want to work out the X-intercepts, which is where the graph will intersect the x-axis. The key observation here is, when you're on the x-axis, the y value will always be 0. Thus the x-intercepts are obtained by setting the y variable, which is given by f of x, to be 0. This will then give rise to a quadratic equation, which you must then attempt to solve using an appropriate method, usually either factorization or the quadratic formula. For this module, we assume you are familiar with these methods. Here, by setting f of x to be 0, we get the following quadratic equation. You should pause the module right now and verify that there are actually no solutions to this equation. Indeed, if you try to factorize the left-hand side, you will not be able to find two numbers which multiply to give the constant term 3, but add to give the middle coefficient 2. And if you try and use the quadratic formula, you'll discover that the inside of the big square root will be a negative number, which means there will be no real solutions for x. This actually means that there are no x-intercepts. So that the graph will not cut the x-axis at all. So putting it all together, we have a concave up, or smiley face parabola, with vertex 1, 2, y-intercept 3, and no x-intercepts, since the graph doesn't cut the x-axis at all. Alright, I hope you found that informative, and that you're now feeling more confident in sketching the graphs of functions, particularly quadratics. Because the study of higher-level mathematics is filled with functions, both simple and complicated, knowing what the graph of a function looks like, even if just a rough sketch in your head, will give you important insight into the properties of the function you're studying. And this will prove invaluable when it comes to solving problems. Okie dokie, see you next time.